this person kicking a ball, and she's kicking a ball. It's like really it's projectile motion. We recognize that it might be launched at an angle, but when it gets up to the top, remember, if it was a slingshot shot vertically, the speed of the top would be 0, right? But if you shoot it on an angle, what could we say about the speed of the top? Is it 0? No, not 0. Not 0 at the top. In fact, what I could say is, you know, at the beginning there was an x component to the velocity. Remember from kinematics, there was an x component to the velocity still at the top, right? So the most I could really say is that the speed is minimized at the top. But I could still say, hey, E total at position 2 rather, is equal to EG2 plus EK2. And I could still say, remember we're standing on the foundations of kinematics maybe, that E total 1 is equal to EG1 plus EK1. I could expand that out as mass times acceleration due to gravity times height 1 plus 1/2 mv1 squared. And I could expand this one out as mass times acceleration due to gravity times height 2 plus 1/2 mv2 squared. Is there anything that could zero out on the first one? Yeah, look, it's on the ground. You're right. That guy could zero out because the height is 0. That's 0. Is there anything I can zero out on this expression? Yeah, the height's not 0, speed's not 0, right? It's coasting forward. At the top, it doesn't stay put. It doesn't have an instantaneous stop at the top. So I can't zero anything out. What I really could say is that I could set those two expressions equal to each other. And I could say something like this. I could say E total 1 equals E total 2. And I could say 1/2 mv1 squared equals mass times acceleration due to gravity times height 2 plus 1/2 mv2 squared. And I'm not actually even going to take this to completion. I want to just take an inventory. Because I trust that we could do this, because we've done roller coaster problems already. If we know the mass, if we know the initial speed, if we know all these values, can you see that this is just an equation with one unknown? We should be able to solve for this, right? We could figure out how fast it's going at the top without even acknowledging x and y components from angled projectile problems. And actually, that's kind of nice. That means that, frankly, this looks like it might be even easier than thinking about a kinematics problem. It might be, right? And that's something that I feel okay about. The other thing is, it's not obvious right off the bat, but in this case, I said that the soccer ball has a mass of 0.43 kilograms. Can I point this out? I could solve this even if I didn't know the mass of the soccer ball. Can you guys see that there's, and I'll put it boldly, there's a mass here, here, and here. In other words, every term has the same mass in it. So if somebody hadn't told me the mass of the soccer ball, what could I do to both sides of this equation? Yeah? Yeah, I could divide both sides by m, and that would cancel out m in every term of this expression, which means that even if someone hadn't told me the mass, if I have an m in every term, I can cancel it out, and that means that this would be a mass-independent solution, which is actually important to me, because it means that I could solve it if somebody doesn't tell me that piece of information. Okay, and that might show up in your homework, which is why I bring this up to you. You might have a roller coaster where it doesn't tell you the mass, or you might throw a microphone up in the air and it doesn't tell you the mass, and maybe that showed up in your homework last night. And so this is sort of a tip for you to help you with that kind of thing, okay? So that was a challenge that I left you with in homework, but it might show up again in the future as well. And then people say, well, could I do the same thing when it gets to height 3? Yeah, why not? I'm not even going to show that. I could do the exact same process, setting energies equal to each other, and I could solve for the speed at height 3. So I wanted to put it out there that there's nothing different between a soccer ball being kicked in the air than a roller coaster. You're going to approach it in the same way, and if masses cancel out, amazing, right? Like that makes things easy. I want to take a look at this second situation. And I've got a pendulum here. I actually think I want to solve this one because this one seems different enough from roller coasters that it might be worth it. If I don't talk about the details of a pendulum, as simple as a pendulum seems, and I'll swing a pendulum from the ceiling in class after I'm done this, just to talk more about it. But as simple as a pendulum seems, if I don't talk about this, people are going to get confused when it comes to homework time. Let's just say that I have a pendulum that starts from rest and it swings low. But when it starts from rest, that means that V1 is equal to 0 meters per second. So this is position 1. And then it swings down low. Now the length of the string for my pendulum, I'm just going to call it cursive L, and you can see that the length of this string is 10 meters. So this is a big pendulum, you know? And if this is a 60 kilogram mass on the end of a pendulum string, maybe this is like a wrecking ball. Okay, so this isn't just like a clock pendulum, this is a big pendulum, you know? And it swings low. And as it swings low, obviously, here, I'll draw another line. I'm going to do it in a different color. When it swings low, can you see that the top of the pendulum has gone to the height of the new line? What that means is that when it was in position 1, I'm going to say that it was at height 1. When it's at position 2, and I'll label this as position 2, it's at this lower height. I think I'm going to say that this is a height of 0. That's going to be my 0 line. I'm going to call that my reference line. And then I want to switch hats just a little bit and just talk about triangles. Just talk about geometry. Can you see that these lines that I drew on there, can you see that it's created a right-angled triangle? Now my understanding of trigonometry is that if I know this angle, if I pull my pendulum off to the side by 40 degrees, and I know how long the rope is, that's now my hypotenuse, I should be able to calculate how tall this triangle is. I'm going to give that a new variable. I'm just going to call it y, because I'm not very creative. Just going to call it y. Now keep in mind that the length of the rope didn't change. When this pendulum got down to the bottom position, can you guys see that it's still going to be 10 meters long? It's still the same rope, so I'm still going to say, look, that's an L value equal to 10 meters. Can anybody see how I can calculate the value of H1 here? Look at this. If I can get the Y value, I could subtract from the L value to get the H1 value. See what I'm talking about? I know how to get the Y value because this is a SOHCAHTOA problem. I'm going to say cosine of theta is equal to Y over L, adjacent over hypotenuse. I get Y all by itself, that's going to be L times cosine theta. And, you know, if I didn't go through all this, people would see pendulums and they'd be like, oh my goodness, how do I deal with that, right? That's why I'm spelling it out, okay? So somehow pendulums challenge people more than roller coasters. I don't know why. It seems like a roller coaster should be more complicated, but a pendulum, you got to know the geometry of a pendulum, okay? So y is equal to, yeah, I'll sub in my values, 10 meters times cosine of 40 degrees. And I'm just going to give this to you because I did the math earlier. It was 7.66044 meters. That's how big y is. And just sort of thinking ahead, I said that if I know y and I know L, I can get the height difference between the initial position and the final position. In other words, that value is going to be the h1, right? The initial height, if I call the final height 0. So I could say, okay, well, I can see that h1 plus y equals L. Take a look at the picture to make sure that that makes sense to you. If I want to know h1, that means h1 is equal to L minus y. In other words, 10 meters minus the y value. And again, I probably over-rounded my y value, but earlier I didn't over-round it, and I got this ridiculous number, 2.339 meters. You know, like this ridiculous value. I was just like holding on to every digit when I was doing it, you know, just because. So I get my h1 value. I say, well, how am I going to use that? Well, this is just conservation of energy now. I say, hey, Eg1 plus Ek1 equals Eg2 plus Ek2. Now I am back in the same zone as roller coasters and slingshots. Because at the top, this thing wasn't moving, right? So since it wasn't moving, the pendulum was at rest, Ek1 would be 0. Is there anything else I can zero out? Eg2, yeah. At the bottom, we define the bottom position as height of 0. So if h2 is equal to 0 meters, Eg2 is gone now as well. Same idea as roller coasters and slingshots, right? Same principles. We say, okay, mass times acceleration due to gravity times height 1 equals 1/2 mv2 squared. Now, I know that I know the mass of this pendulum. But if I was feeling lazy, what could I do with mass here? Yeah? Yeah, look at that. I don't even have to know the mass. I happen to this time, but I don't need it. It's more information than I even need, because those masses can cancel out if I divide both sides by the same thing. So now I'm down to a situation that's even simpler. AgH1 equals 1/2 v2 squared. And I'm just trying to get that v2 value. How fast is the pendulum going when it gets to its lowest point? And if this really was a wrecking ball, I'd be trying to figure out how fast the wrecking ball is going when it slams into the building. You know, demolition time, right? 2AgH1 equals v2 squared. Square root both sides. Just trying to show all my operations. And I sub in my values, and I say v2 is equal to 2 times 9.81 meters per second squared times h1, which was, we just figured that out, 2.3395569 meters. Just figured it out right up above. That's weird. All square rooted. By the way, if you're checking on the units, meters per second squared times meters is meters squared per second squared, but then we're going to square root it, so the units really will work out to meters per second. Just as a unit check on this one, that everything's all good. And I'm kind of painting myself into a corner here. So can somebody help me out? What's the final velocity? Yes, sir. 45.8. I have a sneaky suspicion you forgot to square root. It's not 45 meters per second. Yep. Nice. 775107. I'm just going to stop there because I ran out of space. 6.7751 meters per second, or approximately 6.78. Is that okay? 6.78 meters per second. And that's not bad. Now, before we leave this, because yeah, there'll be some pendulum problems in your homework, maybe some wrecking ball problems in homework. Before we leave this, I want to zoom in on these two cartoons in the bottom. And if you're looking at it from video, I'll zoom in tight. But if you have it on a paper page, then take a look at this. Make sure this makes sense to you. Think through this comic strip. And the reason I'm showing it as a comic strip is a lot of times when we're thinking through these problems, you want to remember that it's not just a static image you're looking at. Whatever static image you're looking at in your notes or in a homework question is actually meant to represent an animation, right? So you need to understand what's happening at the multiple stages of a pendulum swing in order to really understand the problem. And so here's a comic strip. Make sure you can make sense of this. And then likewise, kind of a cartoony way of thinking about things here. This would be sort of a cartoony way of thinking about projectiles. And make sure that this makes sense to you as well, okay? So if you got the paper copy, you're looking at it, make sure you can make sense of it, okay?